August 9th, 1945. 31,000 feet above the Japanese home islands. Major Charles Sweeney adjusted the oxygen flow in his mask and scanned the instrument panel of his B-29 Superfortress, call sign Bockscar. Through the bombardier's clear nose, glazing ahead of the cockpit, the industrial city of Nagasaki spread below like a topographical map, rendered in miniature by the staggering altitude. The German Luftwaffe officer who'd spent 3 years studying captured American bombers would have found this moment incomprehensible. Every tactical doctrine the Reich developed for bomber interception assumed one immutable truth: enemy aircraft must fly within reach of fighters and anti-aircraft artillery. The fortress doctrine, the altitude ceiling limits, the energy calculations for climbing interceptors, all presumed that physical laws of engine performance and atmospheric pressure would eventually bring bombers down to defendable altitudes. But Bockscar cruised at an concision, operational ceiling, where German Messerschmitt Bf 109 seconds would have struggled to maintain level flight, let alone execute combat maneuvers. More staggering still, this bomber had flown nearly 3,000 miles from its base on Tinian Island, carried a bomb load heavier than anything in the Axis arsenal, and would return home after delivering devastation that would end the Pacific War within days. No fighter in the German or Japanese air forces possessed even half this operational range. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The atomic mission represented the ultimate expression of a strategic bombing philosophy that had rendered Axis air defense doctrine obsolete before the war's midpoint. When Boeing's engineers began designing the B-29 inches 1938, they weren't merely building a bigger bomber. They were creating an aircraft that would operate beyond the physical reach of any defensive system the enemy possessed, delivering unprecedented bomb loads across distances that would have seemed fantastical to pre-war military planners. The numbers told a story of capability so overwhelming that Axis intelligence officers initially dismissed early reports as American propaganda. A fully loaded B-29 weighed 65 tons at takeoff, heavier than 3 German Junkers Ju-88 bombers combined. 4 Wright R-3000, 350 duplex Cyclone engines, each producing 2,200 horsepower, drove the massive bomber to cruise speeds exceeding 300 miles per hour. Total available power of 8,800 horsepower matched that of 4 German medium bombers operating simultaneously. Range statistics proved even more revolutionary. The B-29 could fly 3,700 miles with a 10-ton bomb load, more than enough to strike targets anywhere in the Japanese home islands from bases in the Mariana Islands and return safely. 4. Comparison. The Japanese Nakajima Ki-84 Hayate, considered the finest fighter Japan produced during the war, had a combat range of approximately 350 miles. A B-29 could fly round-trip missions exceeding 7 times that distance while carrying 20,000 pounds of bombs. The operational ceiling told the most devastating story for Axis defenders. B-29 seconds routinely operated above 30,000 feet, with service ceilings reaching 33,600 feet. At these altitudes, atmospheric pressure measured less than 1/3 of sea level density, and temperatures plunged to 50 degrees below 0 Fahrenheit. The thin air provided insufficient oxygen for human consciousness, without pressurized crew compartments or supplemental breathing apparatus. Most critically for defenders, aircraft engines producing adequate power at sea level lost performance dramatically in the stratospheric environment where B-29 seconds operated. German fighter pilots who'd mastered tactics for intercepting B-17 flying fortresses over Europe discovered uncomfortable truths when briefed about B-29 capabilities in late-war intelligence assessments. The Messerschmitt Bf 109G, which could reach 39,000 feet under ideal conditions, required nearly 30 minutes of sustained climbing to reach that altitude, burning fuel at prodigious rates that left minimal time for combat maneuvering at operational ceiling. The Focke-Wulf FW-190A, Germany's other frontline fighter, performed excellently below 20,000 feet but suffered dramatically reduced effectiveness above that altitude, precisely where B-29 seconds cruised comfortably. Japanese defenders faced even grimmer arithmetic. The Nakajima Ki-84, capable of intercepting B-29 seconds theoretically, achieved its maximum performance at medium altitudes. At 30,000 feet, the Hayate's engine produced perhaps 60% of its rated power, dramatically reducing speed, climb rate, and maneuverability. Pilots attempting interception at B-29 cruise altitudes reported difficulty maintaining formation, executing attack runs, and returning to base before fuel exhaustion forced emergency landings. The fundamental problem transcended simple performance statistics. Intercepting high-altitude bombers required fighters to climb rapidly to operational ceiling, locate the target formation while managing oxygen systems and extreme cold, execute attack runs against aircraft, flying at speeds comparable to the fighter's maximum velocity at that altitude, all while maintaining sufficient fuel reserves for descent and landing. The energy management problem alone defeated most interception attempts before pilots fired a single shot. But the B-29's true revolutionary feature, the capability that fundamentally altered strategic bombing doctrine, was its pressurized crew compartments. For the first time in aviation history, bomber crews operated in shirt-sleeve comfort at altitudes where atmospheric conditions would kill an unprotected human within minutes. The forward pressurized compartment housed the aircraft commander, pilot, flight engineer, bombardier, navigator, and radio operator. The rear compartment contained the central fire control gunner and two waist scanner positions. A long, narrow tunnel connected the compartments, allowing crew movement between stations during flight. The tail gunner occupied a separate pressurized position accessible only through an external hatch, isolating him from the rest of the crew during high-altitude operations. This arrangement meant that if the tail section sustained damage requiring emergency access, the aircraft needed to descend to altitudes where crew members could survive without pressurization long enough to reach the isolated gunner. Boeing's engineers understood that pressurization created vulnerabilities alongside its advantages. A single 20mm cannon shell penetrating the pressurized fuselage would cause explosive decompression, instantly filling the crew compartments with fog as moisture in the warm, pressurized air condensed in the sudden pressure drop. Visibility vanished, temperatures plummeted to ambient conditions at altitude, and crew members had perhaps seconds to don emergency oxygen masks before hypoxia caused unconsciousness. To mitigate this vulnerability, standard operating procedure called for depressurizing the bomber before entering defended airspace, where flak or fighters posed serious threats. Crews switched to oxygen masks and electrically heated flight suits, maintaining these uncomfortable conditions throughout the bomb run and initial egress from the target area. Once clear of immediate threats, the aircraft could be repressurized for the long flight home, allowing crews to remove masks and warm themselves in the heated compartments. The pressurization system added weight and complexity that German and Japanese aircraft designers consciously rejected in their bomber development programs. German engineers prioritized performance and payload over crew comfort, assuming that bomber operations would occur at medium altitudes where pressurization wasn't necessary. Japanese designers faced material shortages that made sophisticated pressurization systems impractical even when engineering knowledge existed. American industrial capacity allowed Boeing to pursue the pressurization system despite its complexity and cost. The benefits proved transformative for long-duration missions across the Pacific. Crews flying 8 to 12-hour missions arrived at targets with reduced fatigue, maintained better concentration during critical bomb runs, and returned home in condition to brief intelligence officers thoroughly on mission details. Combat effectiveness improved measurably when crews weren't fighting constant cold, oxygen deprivation symptoms, and physical exhaustion. The defensive armament package represented another revolutionary departure from conventional bomber design philosophy. Rather than manually operated gun positions scattered around the airframe, the B-29 featured a centralized fire control system connecting remote-controlled turrets to gunner stations inside the pressurized compartments. A single gunner could control multiple turrets simultaneously, concentrating firepower against attacking fighters from a position, offering excellent visibility without exposure to wind, cold, or immediate combat dangers. The system employed 4 remotely controlled turrets, 2 above the fuselage and 2 below, each mounting two 50-caliber M2 Browning machine guns. The tail position featured a manned turret with two additional 50-caliber guns, plus one 20mm cannon for engaging rear attackers at extended range. Total defensive armament comprised 10 50-caliber machine guns and one cannon, providing formidable firepower across nearly all approach angles. The General Electric Central Fire Control System used analog computers to calculate lead angles, deflection corrections, and range automatically. Gunners sighted targets through optical systems with precise crosshairs, and the computer adjusted aim point based on target range, closure rate, and aircraft maneuvers. This automated fire control dramatically improved hit probability compared to manually aimed weapons requiring gunners to estimate lead angles through experience and intuition. Japanese fighter pilots, attacking B-29 formations, discovered that the defensive fire proved far more accurate than they'd experienced against other Allied bombers. The centralized control system meant that multiple turrets could track a single attacker simultaneously, concentrating fire from weapons physically separated by dozens of feet along the fuselage. This created intersecting fields of fire that were difficult for attacking pilots to evade, as breaking away from one turret's aim point often meant flying directly into another turret's firing. Solution: but the defensive system carried inherent limitations that became apparent through combat experience. The 50-caliber machine guns, while effective against lightly armored fighters, lacked the destructive power of larger caliber weapons. A Japanese Ki 84 or Ki 44 could absorb multiple 50-caliber hits to non-critical areas and continue attacking. The 20mm tail cannon provided better striking power, but limited ammunition capacity restricted sustained fire. More significantly, the remote turret system proved vulnerable to battle damage in ways that surprised engineers. A single cannon shell penetrating the fuselage could sever control cables, electrical connections, or hydraulic lines serving multiple turrets simultaneously. Damage that would disable one or two guns on a B-17 might render half the B-29's defensive armament inoperative if it struck certain centralized system components. The Wright R-3350 engine represented the bomber's greatest engineering, triumph, and most persistent source of operational problems. The 18-cylinder two-row radial engine produced extraordinary power output from a relatively compact package, enabling the B-29's combination of speed, range, and payload capacity. But this power came at the cost of extreme mechanical complexity and thermal stresses that pushed contemporary metallurgy and cooling technology to their limits. Each R-3350 weighed 2,595 pounds dry, before adding oil, coolant, and accessories. Diameter measured 55 inches, with overall length reaching 76 inches. 2 rows of 9 cylinders each, fired in a precise sequence that required sophisticated valve timing and fuel injection systems. At maximum power output, each engine consumed approximately 1 gallon of aviation gasoline per minute, while generating enough heat to melt the aluminum crankcase if cooling systems failed. The magnesium crankcases, chosen for their lightweight and heat dissipation properties, created catastrophic fire hazards when cracked by combat damage or mechanical failure. Magnesium burns at temperatures exceeding 5,600 degrees Fahrenheit, hot enough to ignite even in the absence of additional oxygen. The aircraft's fire suppression systems, designed for conventional petroleum fires, proved largely ineffective against magnesium fires. Statistics showed that 87% of R-3350 engine fires resulted in loss of the aircraft, as crews had mere minutes to shut down the burning engine and hope the fire didn't spread before consuming critical structures. Engine fires became the leading cause of B-29 losses during the first year of operations, exceeding combat losses to enemy action. Maintenance crews at forward bases in the Mariana Islands worked frantically to identify failure modes and implement modifications, reducing fire risks. Improved engine baffling, revised cooling procedures, and strict operating limits gradually reduced fire incidents. But the R-3350 never achieved the reliability Boeing engineers originally promised. The operational tempo demanded by strategic bombing campaigns meant that even moderately reliable engines failed with disturbing frequency across large formations. A group of 100 B-29 seconds launching on a mission could expect 5 to 10 aircraft to abort due to engine problems before reaching the target, with additional casualties from progressive failures during the mission. Some crews completed combat tours without experiencing serious engine troubles. Others suffered repeated failures that tested pilot skill and crew composure on every mission. Despite these mechanical challenges, the B-29 represented such a quantum leap in strategic bombing capability that American commanders accepted the operational risks and pushed the program forward with remarkable urgency. The Manhattan Project, developing atomic weapons, cost approximately $2 billion. The B-29 program cost more, reaching between $3 and $3.4 billion by war's end, making it the single most expensive weapons program the United States undertook during World War II. Production engineering required 4 main assembly plants operating simultaneously to meet delivery schedules. Boeing facilities at Renton, Washington, and Wichita, Kansas produced the majority of airframes. Bell Aircraft constructed B-29 seconds at a massive new plant in Marietta, Georgia, near Atlanta. Glenn Martin Company added production capacity at Bellevue, Nebraska. Thousands of subcontractors across the United States manufactured components, from Wright engines to landing gear assemblies to the sophisticated central fire control computers. The first XB-29 prototype flew from Boeing Field in Seattle on September 21, 1942, less than 3 years after the initial design contract was awarded. This compressed development timeline, driven by urgent wartime requirements, meant that production aircraft began rolling off assembly lines before testing revealed all the type's inherent problems. Service test aircraft deployed to operational units discovered issues that should have been resolved during extended evaluation programs, forcing modifications to be retrofitted across the entire fleet. 3,943 B-29 seconds were constructed by war's end, with production continuing into 1946 as the Army Air Forces built up post-war strategic bomber strength. Each aircraft contained approximately 40,000 individual components, manufactured at hundreds of facilities and assembled using precision jigs, ensuring interchangeability between aircraft. This modularity meant that battle-damaged bombers could be repaired using components from other aircraft, greatly improving maintenance efficiency at forward bases. The logistics challenge of supporting B-29 operations across the Pacific dwarfed anything attempted in the European theatre. Each bomber required 100 gallons of engine oil, 9,300 gallons of aviation fuel for maximum range missions, up to 20,000 pounds of bombs or other ordnance, 13,000 rounds of 50 caliber ammunition, plus shells for the tail cannon, oxygen for pressurization systems, spare parts for mechanical systems, and crews trained to operate the most complex bomber in operational service. Forward bases in the Mariana Islands required massive construction efforts by Navy Seabee battalions who built airfields capable of handling the heavy bombers before ground combat even concluded on Saipan, Tinian, and Guam. Each base needed runways extending 8,500 feet or more, hardstands for dozens of aircraft, fuel storage facilities holding millions of gallons, bomb dumps stocked with conventional and incendiary ordnance, barracks for thousands of aircrew and ground personnel, and maintenance facilities equipped with specialized tools for servicing complex bombers. The first B-29 landed on Saipan on October 12, 1944, beginning a build-up that would eventually station over 1,000 superfortresses across 5 major airfields in the Marianas. From these bases, American strategic bombing could reach any target in Japan, Korea, Manchuria, or occupied China, fundamentally altering the strategic calculus of the Pacific War. But the path to effective operations proved far more difficult than planners anticipated. Early missions from India and China in mid-1944 exposed severe problems with crew training, maintenance procedures, and tactical doctrine. The first combat mission, flown on June 5, 1944, saw 77 B-29 seconds launched from bases in India to bomb railroad yards in Bangkok, Thailand. 5 aircraft were lost to operational causes before reaching the target, foreshadowing the mechanical challenges that would plague the program. On June 15th, 47 superfortresses, staged through forward bases in China to strike the Imperial Iron and Steel Works at Yawata, Japan, marking the first American bombing raid on the Japanese home islands since the Doolittle raid in April 1942. The mission demonstrated both the B-29's unprecedented reach and its operational vulnerabilities. One aircraft was destroyed on the ground by Japanese fighters after an emergency landing in China. Another fell to anti-aircraft fire over the target. A third, Stockett's rocket, disappeared over the Himalayas during the outbound flight, killing all 12 personnel aboard. These early operations from the China-Burma-India theatre faced insurmountable logistical problems. All fuel, ammunition, and supplies had to be flown over the Himalayas, the hump, as the treacherous air route was known. Each ton of bombs dropped on Japan required approximately 12 tons of supplies flown into China to support the mission, an unsustainable ratio that limited operational tempo severely. Additionally, the B-29 seconds based in China could reach only limited portions of Japan while carrying useful bomb loads. The solution lay in capturing the Mariana Islands, which brought Tokyo within 1,500 miles of American air bases, well within the B-29's combat radius. Operations from the Marianas began in earnest in November 1944, with the first Tokyo raid launched on November 24. Bombing accuracy during these early high-altitude precision raids proved disappointing, with only 12% of bombs landing within 1,000 feet of the target in January 1945. Major General Curtis LeMay, who assumed command of XXI Bomber Command in January 1945, recognized that the precision bombing doctrine developed over Europe wasn't working against Japanese targets. Several factors contributed to poor accuracy. The jet stream, a high-altitude wind phenomenon not fully understood by meteorologists at the time, created winds exceeding 140 miles per hour at B-29 operating altitudes. These winds shattered the tight defensive formations American doctrine relied upon and made precision bombing nearly impossible, as gusts could disperse a formation by miles. Japanese industrial targets differed fundamentally from European factories. Rather than concentrated facilities vulnerable to precision strikes, Japanese war production relied heavily on dispersed cottage industries, where workers manufactured components in small workshops throughout residential areas. Destroying these distributed targets required area bombing rather than precision strikes, a realization that led to the most controversial strategic bombing campaign of the Pacific War. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. LeMay made the radical decision to abandon high-altitude daylight precision bombing in favor of low-altitude, nighttime incendiary attacks against Japanese cities. The new tactics called for B-29 seconds to attack between 5,000 and 8,000 feet, well below their design altitude, carrying maximum loads of incendiary bombs designed to start massive fires in densely packed urban areas, built primarily from wood and paper. The first major firebombing raid struck Tokyo on the night of March 9 through 10, 1945. 334 B-29 seconds participated, dropping approximately 1,600 tons of incendiaries on the capital. The resulting firestorm killed an estimated 80,000 to 100,000 civilians, destroyed 16 square miles of the city, and left over 1 million people homeless. It remains the single most destructive conventional bombing raid in history. Japanese defenses proved largely ineffective against these nighttime low-altitude attacks. Fighter pilots trained for high-altitude interception struggled to locate B-29 seconds flying through darkness at medium altitudes. Anti-aircraft artillery, sighted for high-altitude targets, required hasty redeployment and new firing solutions. The element of surprise and the sheer scale of the attacks overwhelmed defensive preparations. Subsequent raids hit Nagoya, Osaka, Kobe, and dozens of smaller cities throughout the Japanese home islands. By July 1945, American bombers had destroyed more than 40% of the built-up areas in 66 Japanese cities. Industrial production plummeted as factories burned, workers fled, destroyed urban areas, and transportation networks collapsed under sustained interdiction. The human cost of this campaign remains controversial decades later. Japanese civilian casualties from strategic bombing exceeded 400,000 killed and hundreds of thousands more injured or displaced. American strategic bombing doctrine held that destroying war-making capacity justified targeting urban areas where war production occurred. But post-war analysis revealed that Japan's will to resist remained largely intact until the atomic bombings demonstrated America's capacity for near-instantaneous annihilation. For Japanese fighter pilots attempting to defend their homeland against these raids, the experience proved psychologically devastating. Veteran pilots who'd survived years of combat in China and throughout the Pacific encountered an enemy they couldn't effectively engage. The few successful interceptions required extraordinary skill, luck, and determination. Lieutenant Saburo Sakai, one of Japan's leading aces with more than 60 confirmed victories, described engaging a B-29 formation at night near Tokyo in his post-war memoir. Flying a Mitsubishi A6M0, he spent 20 minutes climbing to intercept altitude, only to discover that the bomber's speed advantage at that height meant he had one passing attack before they outran him. His cannon fire damaged one Superfortress, but the bomber continued toward its target, and Sakai lacked fuel for a second attack after his climbing interception consumed most of his reserves. The Nakajima Ki-84 Hayate, Japan's finest fighter by most assessments, theoretically possessed the performance to intercept B-29 seconds effectively. Capable of speeds exceeding 400 miles per hour and operational ceilings matching the bombers, the Hayate should have been the weapon that finally stopped the American air offensive. But theoretical performance assumed properly manufactured aircraft, high-quality fuel, and skilled pilots' resources Japan increasingly lacked by 1945. Progressive deterioration in quality control meant pilots never knew how individual Hayates would perform. Landing gear collapsed unexpectedly. Engines suffered mysterious failures. Even when attempting to intercept B-29 seconds, pilots couldn't be certain they would reach combat altitude before mechanical problems forced them to abort. Fuel quality declined catastrophically as American submarines severed petroleum supply lines from the Dutch East Indies. By mid-1945, Japanese aviation fuel often contained pine root oil extracts mixed with low-octane gasoline, creating a volatile mixture that engines struggled to process. Pilots reported that this degraded fuel reduced engine performance by 20 to 30% compared to pre-war standards, eliminating whatever theoretical performance advantage Japanese fighters might have possessed. The pilot shortage proved even more devastating than material deficiencies. By 1945, the experienced veterans who might have developed effective tactics against B-29 seconds were largely dead, missing, or too exhausted from continuous combat to train new pilots. Replacement pilots arrived at operational units with minimal flight time, inadequate gunnery training, and no experience in the demanding high-altitude operations required for bomber interception. One Japanese pilot, whose after-action report was captured and translated by American intelligence, described his first attempted B-29 interception with painful honesty. He spent 40 minutes climbing to 30,000 feet, becoming hypoxic despite his oxygen equipment due to inadequate flow regulation. By the time he reached intercept altitude, the bombers had already completed their attack run and were departing. He attempted a stern chase, but discovered his fighter could barely maintain the B-29 seconds cruising speed at that altitude. After 15 minutes of futile pursuit, his fuel state forced him to abandon the chase and descend before engine failure stranded him at altitude. The defensive weapons Japanese fighters employed proved inadequate against B-29 seconds' robust construction. Standard armament of two 20mm cannons and two 12.7mm machine guns could destroy lightly built fighters quickly, but required sustained fire to down a superfortress. American engineering philosophy emphasized redundant systems, damage-tolerant structures, and compartmentalized fuel tanks that limited vulnerability to small-caliber weapons. Japanese pilots learned through bitter experience that B-29 seconds absorbed incredible punishment and continued flying. Multiple confirmed accounts describe superfortresses returning to base with one or two engines destroyed, control surfaces shot away, fuselage sections penetrated by dozens of holes, and crew members wounded, yet still capable of controlled flight and landing. This damage tolerance meant that even successful attacks often failed to destroy the target, wasting ammunition and fuel for minimal tactical effect. Ramming attacks, where pilots deliberately collided with bombers using their fighters as guided missiles, became increasingly common as conventional interception proved futile. Special attack units, the Ki-44 Shoki, equipped 23rd, 47th, and 70th Sentai, deliberately trained for ramming tactics against B-29 formations. Pilots approached from angles, minimizing exposure to defensive fire, then dove into the bomber's wing or tail section, hoping the collision would destroy the B-29 while allowing the pilot to parachute to safety. These desperate tactics achieved occasional successes but couldn't be sustained. Each ramming attack cost Japan a trained pilot and scarce aircraft for a single bomber destroyed. American production replaced lost B-29 seconds within days, while Japan required months to train replacement pilots and lacked capacity to replace lost fighters at sustainable rates. German intelligence officers analyzing B-29 capabilities from captured documents and interrogated American aircrew reached sobering conclusions about what this bomber would have meant for the Reich's defense if deployed to Europe. Luftwaffe tactical studies conducted in late 1944 explored hypothetical scenarios involving B-29 operations against German targets. The studies concluded that B-29 seconds operating from British bases could have reached any target in Germany or occupied Europe, while maintaining altitude and speed advantages over German interceptors. The Messerschmitt Bf 109K4, Germany's ultimate fighter variant, achieved a service ceiling of 41,000 feet under ideal conditions, but required more than 25 minutes of sustained climbing to reach that altitude. By the time German fighters reached intercept altitude, the bombers could have completed their attack run and begun their return flight. More troubling for German planners, the B-29's defensive armament negated many of the frontal attack tactics that German aces had perfected against B-17 formations. The centralized fire control system allowed defensive gunners to concentrate fire from multiple turrets on a single attacker, creating the kind of defensive concentration that made frontal attacks suicidal. The addition of a remotely controlled forward turret in later B-29 variants would have eliminated the primary vulnerability German fighters exploited against flying fortresses. German anti-aircraft artillery, the fearsome 88mm Flak system that destroyed thousands of Allied aircraft over Europe, would have struggled against B-29 seconds altitude capability. At 30,000 feet, projectile time of flight exceeded 30 seconds, giving bombers ample time to maneuver after detecting muzzle flashes. Shell velocity decreased with altitude, reducing both accuracy and lethality. The thin air at B-29 operating altitudes meant that fragmentation patterns spread less effectively, requiring direct hits for destruction rather than near misses, sufficient to damage lower-flying bombers. But the most devastating aspect of hypothetical B-29 operations over Europe would have been the bombers' range. German fighters defending the Reich struggled to maintain fuel reserves for sustained combat after climbing to intercept altitude. The B-17 seconds and B-24 seconds attacking Germany operated near the limits of their range, meaning they couldn't maneuver extensively without risking fuel exhaustion before reaching England. B-29 seconds, by contrast, could have reached Berlin from Britain with sufficient fuel reserves to conduct evasive maneuvers throughout the mission and still return safely, fundamentally altering the energy management calculations that governed air combat. The reasons why B-29 seconds never operated over Europe involved strategic priorities rather than technical limitations. By the time superfortresses became available in quantity in mid-1944, the combined bomber offensive had already achieved air superiority over Germany through massed raids by B-17 seconds and B-24 seconds. The Army Air Forces decided that deploying B-29 seconds to Europe would dilute their effectiveness without providing proportional benefits, as existing bombers could already reach German targets. More critically, the vast distances in the Pacific theater demanded long-range bombers in ways that European operations did not. From the Marianas to Tokyo measured 1,500 miles, roughly equivalent to flying from London past Berlin into Poland. Operating B-17 seconds or B-24 seconds at such distances proved impossible with acceptable fuel reserves. The B-29 represented the only bomber in any nation's arsenal capable of sustaining strategic bombing across Pacific distances. The Soviet Union recognized this capability immediately upon examining B-29 seconds that made emergency landings in Soviet territory after bombing raids on Japanese-controlled Manchuria. Rather than return the interned aircraft as international law required, Soviet leader Joseph Stalin ordered the bombers reverse-engineered and copied exactly. Andrei Tupolev and his design bureau spent 3 years measuring every component, analyzing every system, and replicating every design feature of the B-29. The resulting Tupolev Tu-4, designated Bull by NATO, proved functionally identical to the American bomber it copied. 847 Tu-4 seconds were manufactured between 27 TEC, 1947 and 1952, providing the Soviet Union with its first strategic bombing capability and setting the stage for the Cold War arms race. The irony of Soviet pilots flying copied B-29 seconds against American B-29 seconds during the Korean War was not lost on either side. When Chinese and Soviet MiG-15 jet fighters began inflicting serious losses on B-29 formations in 1951, American commanders restricted Superfortress operations to nighttime missions, exactly as Japanese defenders had hoped to do in 1945 but lacked the capability to enforce. The MiG-15, specifically designed to destroy B-29 seconds, represented the evolutionary response to the Superfortress's dominance. Soviet designers created a jet fighter capable of climbing to intercept altitude in minutes, rather than the half-hour required by piston engine fighters, with speed exceeding the bombers by more than 200 miles per hour. Armed with 37mm and 23mm cannons, the MiG possessed the firepower to destroy heavy bombers quickly. But the MiG-15's success came 6 years too late to influence World War II outcomes. During the critical period, from 1944 through 1945, no fighter in Axis service possessed the combination of speed, altitude capability, and firepower necessary to stop B-29 operations. The handful of successful interceptions achieved by Japanese pilots through extraordinary skill and determination represented statistical anomalies rather than replicable tactical successes. American losses to all causes during B-29 operations totaled 512 aircraft in World War II, including both combat and operational losses. Of these, only 147 fell to Japanese fighters and anti-aircraft fire. 267 were lost to engine fires, mechanical failures, takeoff accidents, and other operational causes. The stark ratio, nearly 2 B-29 seconds lost to mechanical problems for every one destroyed by the enemy, illustrated how immature the design remained even after entering combat. But even these losses, while tragic for the crews involved, represented acceptable attrition rates compared to the strategic devastation the bombers inflicted. B-29 seconds flew approximately 33,000 combat sorties during the war, producing an overall loss rate of 1.38%. For comparison, B-17 operations over Germany in 1943 experienced loss rates approaching 10% on some missions, losses that would have halted operations if sustained. Crew survival rates following B-29 losses demonstrated another advantage of the bomber's advanced design. The pressurized compartments, while vulnerable to battle damage, provided crew areas large enough for parachutes and emergency equipment. The aircraft's structural strength meant that catastrophic breakups remained relatively rare compared to smaller bombers. When B-29 seconds were shot down over Japan, survival rates for crews who successfully bailed out approached 50%, far higher than crews in less robust aircraft. However, captured American air crews faced horrific treatment at Japanese hands. International law supposedly protected prisoners of war from execution or torture, but Japanese military authorities frequently disregarded these protections, particularly for air crews whose bombing missions killed Japanese civilians. Multiple documented cases exist of B-29 crews being executed after capture, including beheadings, bayoneting, and in some instances, medical experimentation. One particularly horrific incident occurred on May 24, 1945, when 9 crewmen from a downed B-29 were taken to Kyushu Imperial University, where 8 of them were subjected to vivisection experiments conducted by medical officers. The sole survivor testified at post-war trials, leading to convictions for war crimes. Such atrocities created an atmosphere where American crews preferred death in combat to capture, understanding that surrender offered little hope of survival. The atomic missions in August 1945 represented the culmination of the B-29 program's strategic purpose. The bombers that struck Hiroshima and Nagasaki, modified to silverplate specifications for carrying nuclear weapons, demonstrated capabilities no other aircraft possessed. The missions required flying more than 3,000 miles round-trip, delivering a single bomb weighing nearly 10,000 pounds, and returning safely to base exactly the mission profile Boeing engineers designed the B-29 to accomplish. Enola Gay, piloted by Colonel Paul Tibbets, dropped Little Boy on Hiroshima at 8:15 a.m. on August 6. The uranium-235 gun-type device detonated with an explosive yield equivalent to 15 kilotons of TNT, instantly killing an estimated 70,000 people and injuring 70,000 more. The bomber escaped. The blast wave through a dramatic diving turn that placed nearly 10 miles of distance between the aircraft and the detonation point within the critical seconds following weapon release. 3 days later, Bockscar, with Major Charles Sweeney at the controls, delivered Fat Man to Nagasaki after finding the primary target of Kokura obscured by clouds. The plutonium implosion-type weapon yielded approximately 21 kilotons, killing an estimated 40,000 people immediately, with tens of thousands more dying from radiation exposure in subsequent months. Japan surrendered on August 15, 1945, following Emperor Hirohito's radio address, acknowledging that the war situation has developed not necessarily to Japan's advantage, and citing a new and most cruel bomb as justification for Clay's capitulation. Debate continues regarding whether the atomic bombings were necessary to end the war or whether Japan would have surrendered due to conventional bombing and blockade, but the B-29's role as delivery vehicle proved historically undeniable. The strategic bombing campaign conducted by B-29 seconds destroyed Japanese industrial capacity, killed hundreds of thousands of civilians, displaced millions more, severed transportation networks, and eliminated petroleum refining capability. By August 1945, Japan's military forces lacked fuel for training flights, food supplies for troops approached starvation levels, and war production had essentially halted. The home islands faced invasion by American forces, who had already demonstrated overwhelming material superiority throughout the Pacific campaign. Whether conventional strategic bombing alone would have forced surrender without atomic weapons remains one of history's great counterfactuals. What stands beyond dispute is that the B-29 Superfortress achieved its designed purpose, delivering unprecedented bomb tonnage across distances no defensive system could counter, fundamentally altering the strategic calculus of modern warfare. The lesson that Japanese and German military planners learned too late was that modern industrial warfare had become as much about production capacity as battlefield tactics. No amount of pilot skill, tactical innovation, or defensive preparation could compensate for the overwhelming disparity in aircraft performance and range that American engineering and manufacturing achieved with the B-29. German Luftwaffe officers studying captured B-17 seconds in 1943 understood they faced industrial advantages they couldn't match. But the B-17, impressive as it was, still operated within the theoretical engagement envelope of Axis fighters and anti-aircraft systems. The B-29 transcended those limitations entirely, creating a weapon system that operated beyond reach of any defensive countermeasure the enemy possessed. The range statistics tell the story most dramatically. A fully loaded B-29 could fly 3,700 miles to strike targets and return from distances where no fighter could follow. The Japanese Nakajima Ki-84, with its combat range of 350 miles, couldn't escort friendly bombers to American bases, even if Japan possessed bombers with equivalent range. German fighters faced identical limitations, unable to operate effectively more than 200 to 300 miles from their bases. This fundamental asymmetry, American bombers reaching targets anywhere in enemy territory while Axis fighters operated within small defensive radii, meant that strategic initiative rested entirely with American forces. They chose when, where, and how to attack, while defenders could only react to raids they often detected too late to intercept effectively. The pressurization system, initially seen as a luxury feature by critics questioning its cost, proved decisive in maintaining this advantage. Crews operating in shirt-sleeve comfort at 30,000 feet arrived at targets alert and capable of comforting. Precise execution. Axis fighter pilots, struggling to maintain consciousness through inadequate oxygen systems while enduring temperatures 50 degrees below zero, fought fatigue and hypoxia alongside enemy aircraft. The cost of developing this capability over $3 billion, more than the Manhattan Project, seemed extravagant to some critics, until combat operations demonstrated that B-29 seconds accomplished missions no other aircraft could attempt. The investment purchased not just individual bombers, but an entire system of strategic reach that fundamentally altered warfare. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.